The International Space Station circles Earth so smoothly that it can seem motionless, suspended above the planet, like a light in the dark. But it is not floating, and nothing is supporting it from below. At every moment, the station is falling toward Earth under the strong pull of gravity, moving fast enough to keep missing the surface as the planet curves beneath it. Even at roughly 400 kilometers above us, traces of atmosphere still brush against its structure, stealing a little speed and lowering its orbit. Without carefully timed engine burns, the station would not remain there forever. So tonight, the question is simple. Why has the International Space Station still not fallen back to Earth? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If you could watch one complete orbit from the station's window, which place on Earth would you wait to see below? Let me know in the comments. I will pin the most creative answer. Tonight, you are watching the Just About Space channel, talking about why the space station still hasn't fallen back to Earth. On a clear evening, the International Space Station can sometimes be seen without a telescope. It appears as a bright point moving steadily across the sky, faster than an aircraft and without the blinking lights that usually reveal one. There is no visible trail behind it, no engine flame, and no sound arriving from above. For a few minutes, it crosses the darkness with such calm precision that it can seem almost fixed to an invisible path. Sometimes it moves into Earth's shadow. Sometimes it disappears below the horizon. The light is gone, but the station continues around the planet, carrying its crew through another sunrise less than an hour later. In reality, the station is traveling at roughly 28,000 kilometers per hour. It circles Earth in about 90 minutes, passing from daylight into darkness and back again many times during a single day. At that speed, cities, oceans, deserts, and entire countries move beneath it in minutes. A crew member looking through the window may watch the Mediterranean pass below, then see the Middle East, India, and the Pacific before most people on Earth have finished an ordinary meal. Inside, loose objects drift quietly. Astronauts move with slow pushes from walls and handrails. Water forms floating spheres. The large windows reveal Earth turning below, with no vibration of wheels, no wind against the glass, and no road to show how quickly the landscape is changing. No trees, clouds, buildings, or mountains rush alongside the station. The stars are too distant to shift visibly, while Earth fills much of the view beneath it. That stillness can create the impression that the station is resting above the planet. Nothing supports the structure from below. There are no cables holding it in place, no invisible platform beneath its solar arrays, and no point in space where Earth's gravity has disappeared. The station remains close enough to the planet that gravity is still powerful. If it was somehow placed at the same altitude without its enormous sideways speed, it would fall. Earth would pull the station downward in the same basic way that it pulls a dropped object toward the ground. The reason the station does not arrive at the surface is not that it has escaped gravity. It is because it is moving sideways so quickly that the surface curves away beneath it. The station is always falling. Its path is continuously bending toward Earth, but the planet is round. As the station falls, it also travels forward. The surface drops away at nearly the same rate that the station descends toward it. Instead of striking the atmosphere below, the station moves around the curve of the world. From far away, the result looks like a smooth circle around Earth. From the station's point of view, there is no feeling of turning around the planet in the way a car turns around a corner. The station does not need to point its nose into the turn. It does not bank like an aircraft. It follows the curved route created by its speed and Earth's pull. The station stays above Earth because it is falling toward Earth. Without it, the station would not continue circling the planet. It would travel away in a straight line, leaving Earth behind. The same force that keeps people on the ground keeps the station moving around the world. A stone dropped from a hand falls nearly straight downward because it has little sideways motion. Throw the stone forward, and it travels some distance before reaching the ground. If it could be launched fast enough above the atmosphere, the surface would curve away before the stone reached it. The stone would keep falling around Earth. Earth is enormous, and its curvature is gentle when seen from the surface. A person standing on the ground cannot watch the landscape fall away beneath a moving object. From orbit, that curvature becomes part of the station's path. During every second of flight, the station travels several kilometers forward. At the same time, gravity bends that motion downward, just enough to keep the structure near the planet. If the sideways speed were much lower, the path would curve too sharply and enter denser layers of the atmosphere. If the speed were higher, the station could move into a wider orbit. At a great enough speed, an object could escape Earth entirely. It is moving too fast to fall directly onto the planet, but not fast enough to leave Earth behind. The path exists only as the result of motion. Every part of the station follows it together: the laboratories, sleeping areas, solar arrays, radiators, visiting spacecraft, air inside the modules, and the astronauts themselves. The floor is falling at the same rate as the person above it, so it never rises to support their feet. On Earth, the sensation of weight comes mainly from the ground, preventing the body from falling. Gravity pulls downward, but the floor pushes upward. A crew member can release a tool, and both continue along nearly the same orbital path. The tool appears to hover, although it is moving around Earth at the same tremendous speed as everything else. A glass of water cannot sit on a table because there is no lasting downward direction inside the cabin. Droplets leave the container and remain nearby, shaped mostly by surface tension. Sleeping bags can be attached to walls or ceilings because those directions have little practical meaning. The strange calm of the cabin is the physical experience of continuous free fall. Gravity is still present, and the station is large enough that small differences exist across it. Vibrations, air movement, equipment, and slight forces from atmospheric drag also disturb the perfect state. But for daily life aboard the station, the effect is close enough to weightlessness that astronauts can work in 3 dimensions. A gentle push can carry someone across a module, while a stronger push may send them into the opposite wall faster than expected. Almost everything must be attached, stored, or held in place. Equipment covers surfaces in every direction. Workstations may appear overhead from one angle and beneath the feet from another. Astronauts often choose a common orientation for comfort, but the station itself does not provide one. Earth below may give the eyes a sense of down, yet the body feels no matching pull toward the floor. The inner ear evolved under constant gravity. It expects movement and orientation to produce familiar signals. An astronaut may see a wall as the floor, turn around, and suddenly experience the room differently. Over time, the brain adapts. The floor begins supporting the body again. Objects fall when released. Muscles and bones must carry loads they have not experienced during the mission. Without the usual resistance of gravity, some muscles are used less. Exercise becomes a daily necessity, not only for fitness, but to reduce the physical changes caused by long exposure to microgravity. Even while the station seems calm, the human body is responding to an environment for which it was never designed. It gives researchers long periods of microgravity without sending a spacecraft far from Earth. The station remains close enough for crews and supplies to reach it, yet it falls freely enough for experiments to behave differently from those on the ground. Fluids do not settle naturally at the bottom of containers. Crystals can form in ways that are difficult to reproduce under ordinary gravity. Its value comes from remaining close to Earth, while never standing still above one place. The ISS is not in the kind of orbit used by communication satellites that appear fixed over the same region of the planet. Those satellites travel much farther away and require about 1 day to complete an orbit, matching Earth's rotation. The space station is much lower and moves around Earth far more quickly. A person on the ground sees it only when the orbit carries it overhead at the right time and sunlight reflects from its structure. Minutes later, it is already moving beyond the horizon. The station's path is tilted relative to the equator, allowing it to pass over a wide range of latitudes. It does not circle directly above one line on a map. Earth rotates beneath the orbit, so each pass crosses a different set of places. Over time, the station travels above much of the inhabited world. This moving relationship explains why crews see so much of the planet. Coastlines, storms, rivers, mountain ranges, and city lights appear beneath them in changing combinations. The station may pass over one region during daylight and return hours later when darkness has arrived. 16 sunrises and sunsets can occur during a single day aboard the ISS. Each one comes from the station crossing rapidly between sunlight and Earth's shadow. The sun does not rise slowly above a fixed landscape. It appears at the curved edge of the planet, lighting thin layers of atmosphere in orange, blue, and pale white. Then daylight returns, and the surface below becomes visible again. The view is beautiful because the station is moving through a carefully maintained path, but that path is not perfectly permanent. The ISS is often described as though it has been placed in orbit and simply left there. In reality, no low Earth orbit remains unchanged forever. Earth is not a perfect sphere. Its mass is not distributed with perfect uniformity. The Moon and Sun exert smaller gravitational effects. The station adjusts its orientation, visiting vehicles arrive and depart, and the thin upper atmosphere creates drag. The orbit slowly changes. Calculations and engine burns keep it useful. Even the station's large size matters. Its solar arrays stretch across a wide area, catching sunlight and generating electricity. They also present a broad structure to the thin atmosphere through which the station moves. The gas at this altitude is almost unimaginably sparse, but the station travels through it at orbital speed. Individual molecules strike the outer surfaces. Each collision has almost no effect. Across the full structure, repeated continuously, the collisions gradually remove energy from the orbit. The station slows by a tiny amount. When an orbiting object slows, it does not simply remain at the same altitude. While moving more gently, its path begins dropping closer to Earth. The lower region contains slightly more atmospheric material, increasing the drag. Without correction, the process continues. This does not mean the ISS is about to fall without warning. Its altitude is monitored closely, and visiting spacecraft can perform reboost maneuvers that restore some of the lost energy. But the station is not resting on a permanent shelf above the atmosphere. It is balanced inside a changing environment. The same orbit that makes microgravity possible is always being weakened by the last traces of air. From the ground, none of this can be seen. The bright point moves smoothly across the sky. There is no visible sign that its altitude changes, no indication of the engine burns that occasionally raise it, and no way to sense the constant calculation behind every pass. The station looks simple because distance hides the work required to keep it there. Its movement is predictable enough that people can step outside at the right moment and watch it cross above them. That predictability can feel like permanence, yet every pass is part of a fall that must remain carefully shaped. The station has completed tens of thousands of orbits, but it has never stopped falling during any of them. Every sunrise aboard begins while Earth is pulling the entire structure downward. Every experiment is performed inside that fall. Every sleeping astronaut circles the planet because the floor beneath them is falling too. The ISS stays above Earth, not by resisting gravity, but by surrendering to it in exactly the right way. The danger appears when that balance changes. Too little speed allows the path to dip lower. Denser atmosphere removes more energy. The station moves closer to the point where its orbit can no longer be maintained. The process is slow enough to control, but real enough that it can never be ignored. Understanding why the space station has not fallen back to Earth, therefore begins with a stranger truth and simple suspension. It has been falling since the moment it entered orbit. And the answer lies in how forward motion can transform a descent toward the planet into a path that continues around it. A falling object does not need to move straight down. The direction of its fall depends on the motion it already has. A stone released from a hand drops almost vertically because it begins with little horizontal speed. Throw the same stone forward, and gravity still pulls it toward the ground, but the stone travels farther before it lands. Increase that speed, and the path becomes longer and flatter. The stone is not resisting gravity. Gravity continues bending its motion downward every second. The difference is that the surface of Earth is curved, and at a high enough speed, the ground begins to fall away beneath the object almost as quickly as the object falls toward it. This is the geometry of orbit. The International Space Station travels forward at roughly 28,000 kilometers per hour. During a single second, it crosses several kilometers above the planet. Gravity bends that motion toward Earth, but the surface curves away below. The station misses the ground. A moment later, gravity bends the path again. The station misses the ground again. This happens continuously, not as a series of separate corrections, but as one smooth motion around the planet. The orbit is therefore not a circular road placed in space. It is the shape created when forward speed and gravitational fall remain in balance. If gravity vanished suddenly, the station would not continue circling Earth. It would leave the curved path and travel along a straight line, moving away from the planet. If its forward speed vanished instead, the station would fall nearly straight downward. Its orbit exists only because both conditions are present at once. The forward motion prevents an immediate impact. Gravity prevents the station from escaping in a straight line. Together, they create a path that can continue around Earth again and again. This relationship can be difficult to picture because life on the surface hides the curvature of the planet. A road seems flat. The horizon appears distant but level. A thrown object always reaches the ground before Earth's roundness becomes important. Orbital speed changes that. At the altitude of the station, the vehicle moves forward so far during every second that the curve of the planet becomes part of the fall. The station is never flying over a flat surface. It is moving around a sphere. This is why simply moving upward is not enough to enter orbit. A rocket must gain altitude to leave the thickest parts of the atmosphere, but it must also turn and build enormous sideways speed. Much of the energy required for orbit is used not to climb higher, but to move faster around Earth. A vehicle that rises hundreds of kilometers and then stops accelerating sideways has not entered a stable orbit. It has only reached a high point in a long fall. Gravity will pull it back. To remain above Earth, the spacecraft must arrive at the correct altitude with enough horizontal speed for the curved fall to continue around the planet. The rocket turns farther toward the horizon and accelerates sideways. In reality, that sideways motion is what allows it to stay there. In orbit, changing speed also changes the shape and period of the path. The station follows the same rules. Its orbit is not a perfect circle and does not remain exactly the same from one day to another. The altitude rises and falls slightly along the path. Gravitational differences, atmospheric drag, visiting spacecraft, and planned maneuvers all change the motion by small amounts. Yet the underlying balance remains clear. The station moves forward while gravity constantly turns that movement downward. The result is a path around Earth rather than into it. The speed required depends on altitude. Close to Earth, gravity is strong and the orbit is relatively small, so a spacecraft must move quickly to keep missing the surface. Farther away, an orbit becomes larger, and the required speed becomes lower. The Moon travels much more slowly around Earth than the station does, because it is vastly farther away. It takes about a month to complete one orbit, while the ISS requires roughly 90 minutes. Both are falling around Earth. Their distances and speeds are simply different. The International Space Station is far too low and fast for this effect. It passes over changing parts of Earth while the planet rotates beneath it. The station is high enough to orbit freely, yet still close enough for gravity to remain only moderately weaker than at the surface. Astronauts do not float because gravity has become faint. At the station's altitude, Earth still pulls strongly. The important difference is that the station is allowed to fall. On the ground, a person cannot follow a gravitational path freely because the surface interrupts the fall. The floor pushes upward against the feet. A chair pushes against the body. These supporting forces create the familiar sensation of weight. Inside the ISS, the station and everything within it are moving along almost the same freefall path. The walls do not need to hold the astronauts above Earth. The walls are falling with them. Gravity provides that inward acceleration. The station is always moving forward and always accelerating downward. This is why an orbit can continue without engines firing constantly. Once the station has the required speed, gravity bends the path naturally. Engines are needed to reach orbit, adjust it, replace energy lost to drag, avoid debris, and control orientation. They are not required to hold the station up every second. The station is not hovering like a helicopter. A helicopter must produce lift continuously because it remains in nearly the same place above the ground while gravity pulls downward. If its engines stop, it descends. The ISS does not remain above one location. It moves around the entire planet so quickly that its fall becomes orbital. If every engine aboard was silent, the station would continue circling Earth for a time. Its immediate motion would change very little. The long-term problem comes from atmospheric drag, not from the absence of constant upward thrust. This difference explains why objects can orbit for years even after their engines stop working. A satellite may receive one final push into the correct path and then coast around Earth. Gravity continues shaping the orbit, while the vacuum provides very little resistance. The object is still moving because there is almost nothing to slow it significantly. Low Earth orbit is not a perfect vacuum, so the station does lose energy gradually, but the process is slow compared with ordinary falling near the ground. The word falling can therefore be misleading if it creates the image of a rapid downward plunge. Orbital fall is continuous and curved. The station descends toward Earth in the gravitational sense, while maintaining nearly the same average altitude because it travels around the planet. Its fall has no bottom as long as the speed remains sufficient and drag is corrected. This can be expressed through energy as well as motion. The station possesses gravitational potential energy because it is high above Earth, and kinetic energy because it moves so quickly. An orbital maneuver changes the relationship between them. When engines add speed, the station initially moves faster and begins climbing into a higher path. As it rises, some kinetic energy becomes gravitational potential energy, and the final orbital speed in the higher orbit can actually be lower than before. This is another result that feels strange from the perspective of surface travel. An engine burn that increases speed can eventually place a spacecraft into a higher orbit where it moves more slowly. A burn that reduces speed can lower the orbit, where the spacecraft later moves faster before atmospheric drag becomes important. The path changes as the vehicle trades motion and altitude under gravity. Mission controllers use these relationships carefully. A reboost burn is timed and directed so that the station reaches the desired orbital range. A visiting spacecraft approaching the ISS performs a sequence of burns. each one creating a new orbit that brings the two vehicles closer at a planned time. Nothing can be treated as a simple straight-line journey. Every movement becomes part of a larger curve around Earth. Even small actions aboard the station technically influence its motion. When an astronaut pushes against a wall, the astronaut moves one way and the station shifts an unimaginably small amount in the other. Equipment changes position. Robotic arms move cargo. Visiting vehicles dock and alter the combined mass and balance of the structure. These effects are tiny compared with the station's orbital momentum, but they reveal that the ISS is not a fixed object placed inside an orbit. It is a moving physical system whose parts exchange forces while the entire structure falls around Earth. Its orientation must also be controlled. The station normally keeps a planned relationship with Earth, the direction of travel, and the Sun. This allows solar arrays to generate power, radiators to release heat, antennas to communicate, and instruments to point correctly. Small thrusters, gyroscopes, and visiting spacecraft help manage this orientation. The orbit determines where the station goes. Attitude control determines how the station faces while going there. These are separate problems. A spacecraft can follow the correct orbit while slowly rotating in an unwanted way. The ISS must manage both because its structure is large, complex, and covered with systems that depend on direction. Solar arrays track the sun. Radiators must release heat efficiently. Docking ports need to be positioned for arriving vehicles. Windows and cameras are used to observe Earth. The station's motion through orbit is natural once established, but living and working within that motion requires constant control. The apparent simplicity of one bright point crossing the night sky hides all of this. What looks like a straight passage overhead is part of a curved route around the planet. What seems like steady motion is continuous acceleration. What appears to be suspension is a fall. What feels like weightlessness inside is the shared experience of that fall. This is why a photograph of the station can be deceptive. A still image freezes the solar arrays against black space and makes the structure look parked above Earth. Nothing in the frame shows 28,000 kilometers per hour. Nothing shows the planet curving away below fast enough to prevent impact. The orbit becomes visible only through time. Watch the station for several minutes, and it crosses a large section of the sky. Wait roughly an hour and a half, and it has traveled around the world. Follow it for one day, and it has completed about 16 orbits. The movement is enormous, yet the cabin remains calm because every part shares it. There is no sudden force pressing astronauts backward, as there would be during continuous acceleration from an engine. Once established in orbit, the station and crew coast together. Gravity changes their direction, but because it acts on the entire system, the occupants do not feel it as a supporting force beneath them. This leads directly to the familiar images of astronauts floating. A person releases a pen, and the pen remains nearby. A drop of water forms a sphere. Food must be secured. Sleeping bags can be attached to different surfaces because no floor has a permanent claim to the body. These scenes are often described as life without gravity. They are actually scenes of gravity acting freely. Earth is pulling on the station, the astronaut, the pen, and the water at the same time. The reason they appear to float is not that the pull has vanished, but that nothing inside the cabin is preventing their shared descent. Understanding orbit therefore changes the meaning of weightlessness. It is not an escape from Earth's gravity. It is the most complete surrender to it. And once the station's forward speed had turned its fall into a path around the planet, the floating world inside could be understood as the result of the station, its crew, and every loose object, sharing that same continuous descent together. The word weightless can make the scene seem simpler than it is. It suggests that gravity has disappeared, leaving the astronauts beyond Earth's reach. But at the altitude of the International Space Station, gravity is still close to 9/10 as strong as it is at the surface. On the ground, the floor stops the body from following gravity. It presses upward against the feet, the legs, and the spine. That support is what creates the familiar sensation of weight. Inside the station, the floor does not stop the fall, because the floor is falling too. The walls, equipment, air, tools, and people all move along nearly the same curved path around Earth. A released object does not drop toward one side of the cabin. It remains close because both the object and the station continue falling together. This is why the better word is microgravity. Gravity is present, but the usual support forces are almost absent. Small differences remain because the station is large, its orbit is not perfectly smooth, and faint forces continue acting on it. Yet for the crew, the result is a world where no direction stays naturally down. A person can move through a module with one gentle push. The motion may continue farther than expected because there is no floor friction to slow it. Stopping requires a handrail, a wall, or another carefully placed push. A strong push can send someone across the cabin too quickly. A careless turn can lead to an unexpected collision with equipment. Astronauts learn to move slowly, using their fingertips and handrails rather than treating the station like a room on Earth. What appears above one astronaut may be beneath another. Computers, storage bags, cables and experiments cover surfaces in every direction. Crews often agree on a shared orientation because the mind prefers one. Labels are placed to be read from that common viewpoint, and photographs usually make the modules appear more familiar than they truly are. On Earth, the fluid and tiny structures inside the inner ear help the brain sense acceleration and orientation. They evolved in an environment where gravity always points toward the ground. A newly arrived astronaut may turn their head and feel as though the room has moved. The eyes report one orientation, while the balance system provides no matching sense of weight. This can cause space motion sickness during the first days of a mission. The symptoms usually fade as the brain adapts. What first feels unnatural slowly becomes ordinary. The return to Earth later can be more surprising. After months of moving without weight, the floor suddenly supports the body again. The head feels heavy. Objects fall when released. Walking requires balance and muscle effort that the nervous system has partially learned to ignore. Inside the station, daily life is shaped by the shared fall. Sleeping does not require a bed, because the body does not settle onto a mattress. Astronauts use sleeping bags attached to a wall or another surface so they do not drift into equipment during the night. A crew member can sleep upright, sideways, or in a position that would be impossible to maintain comfortably on Earth. There is no weight pressing the body against one surface, although ventilation remains important because warm exhaled air does not rise away naturally. Fans run throughout the station to keep the atmosphere circulating. Their quiet mechanical sound becomes part of life aboard the ISS. Food cannot be placed casually on a plate. Containers, packets, and utensils must be held or attached so they do not drift away. Crumbs are avoided because small pieces could float into vents, instruments, or eyes. Liquids remain inside sealed packages and are drawn through straws. Surface tension pulls it into a rounded shape, and the sphere can float through the cabin until it touches another surface or is collected. Water reveals the difference between gravity and the smaller forces that normally hide beneath it. On Earth, gravity pulls a drop downward and spreads a puddle across a surface. In orbit, surface tension becomes more obvious because there is almost no lasting downward pull relative to the station. The same effect can make water cling to skin, form moving bubbles, or wrap itself around an object. On Earth, hot gases rise while cooler air moves in below. This creates the familiar upward shape of a flame. Inside microgravity, hot gas does not rise in the usual way. Oxygen reaches the flame more slowly through diffusion, and the burning region can become rounder and weaker. The absence of normal convection changes temperature, soot production, and the way combustion spreads. Future spacecraft and habitats must be designed for fires that may behave differently from those on Earth. Smoke does not automatically rise toward a ceiling, because the cabin has no natural ceiling. The station allows these dangers to be studied in a controlled environment, while Earth remains close enough to provide support. Plants also respond to the missing sense of down. On Earth, roots generally grow with gravity, while stems grow against it. In orbit, plants rely more heavily on light, moisture, and internal chemical signals. Water does not drain through soil in the same way. It can remain around roots and prevent enough oxygen from reaching them if the system is not carefully controlled. Growing even a small plant requires an environment designed around the behavior of fluids in microgravity. Plants can help researchers understand how living systems adapt when one of Earth's most constant forces no longer provides direction. The heart no longer works against gravity in the usual way. Fluids that normally gather more strongly in the legs shift toward the chest and head. The body interprets the fluid shift as though it contains too much liquid and begins reducing the total amount. These changes are manageable in orbit, but they become important when the crew returns to Earth. A body adapted to weightlessness may struggle to maintain blood pressure when standing again. Without careful preparation, a person can feel dizzy or faint. Astronauts spend a significant part of each day using specially designed machines that provide resistance without ordinary weights. Instead, devices use vacuum cylinders, flywheels, cables, and other systems to create forces the muscles must work against. Running also requires a harness that holds the body onto a treadmill. Without regular loading, muscles weaken and bones lose mineral density because the body no longer receives the same mechanical signals it experiences on Earth. The spine can lengthen slightly when the vertebrae are no longer compressed by body weight. Some astronauts become temporarily taller in orbit and may experience back discomfort as the body adjusts. Bones, muscles, circulation, balance, and even the sense of orientation developed under a force that never stopped acting. The station does not remove that force, but its shared fall removes the body's usual resistance to it. The side of the ISS closer to Earth is being pulled slightly more strongly than the side farther away. The station is large enough for this difference to exist, although it is tiny. Objects released in different parts of the cabin do not follow perfectly identical paths forever. Air currents, fans, vibrations, crew movement, and the station's rotation can slowly carry them away. A floating object may appear still for a moment, then drift toward a wall. This is why microgravity is not perfect, zero gravity. The environment contains weak accelerations from many sources. Visiting spacecraft dock. Thrusters fire. Robotic arms move. Crew members push against handrails. Equipment vibrates. The station passes through faint traces of atmosphere that slow its outer surfaces. Each effect is small, but sensitive experiments can detect them. Researchers sometimes schedule certain work during quieter periods, when disturbances are reduced. Even the movement of the crew can matter. The ISS is both a home and a laboratory, so complete stillness is impossible. Microgravity experiments are designed around the fact that the platform is always alive with motion. Some investigations use this environment to observe processes that gravity normally hides. Molten materials can be studied without settling heavily against a container. Protein crystals can sometimes grow with fewer gravity-driven disturbances. Fluids can be mixed, separated, heated, or cooled, while scientists watch the smaller forces become dominant. These experiments are not valuable because space makes every result better. They are valuable because space changes the rules enough to reveal different parts of the same physical process. Gravity on Earth can cause heavier material to sink and lighter material to rise. It drives convection, sedimentation, and pressure differences. In microgravity, those effects become much weaker. Diffusion, surface tension, electrical forces, and molecular interactions can shape the result more clearly. The station becomes a place where familiar materials behave in unfamiliar ways, not because they have changed, but because one overwhelming influence has been quieted. The same is true for the astronauts. A person who appears to float freely is not outside the control of gravity. The person is following gravity more completely than anyone standing on the ground. Nothing stops the descent. No surface interrupts the path. The entire station moves with the body, preserving the illusion that the body is still. This is why a loose tool can remain beside an astronaut, while both travel thousands of kilometers. They share nearly the same speed, direction, and gravitational acceleration. From inside, the motion disappears. From Earth, the pair circles the planet in 90 minutes. The difference between those viewpoints is one of the strangest parts of orbital life. An astronaut can look calm while moving faster than a rifle bullet. A drop of water can appear motionless while crossing continents. A sleeping crew can pass through several national borders in minutes without feeling a turn. The station's speed is enormous, yet almost every nearby object shares it. Motion becomes visible only in the planet below. Cloud systems slide toward the horizon. Coastlines arrive and disappear. Daylight becomes darkness, then returns. Earth provides the reference that the cabin lacks. Without the view below, the crew could feel as though the station were drifting quietly in one place. The windows reveal that the floating interior belongs to a vehicle racing around a curved world. They also reveal how close the station remains to Earth. The atmosphere appears as a thin, colored line along the horizon, delicate enough to seem like a surface rather than the deep ocean of air experienced from the ground. The station flies above most of it, but not beyond all of it. This distinction is easy to miss. The darkness outside looks like deep space. Stars remain visible. The black background gives no sign of wind or weather. Yet the upper atmosphere continues upward, far beyond the layers where aircraft can fly. At the station's altitude, the remaining particles are rare, but the ISS meets them at tremendous speed. The station's broad solar arrays, radiators, modules, and truss structure pass through this thin gas during every orbit. One collision has no meaningful effect. Billions of collisions across a large surface slowly remove energy from the motion. The same continuous fall that creates weightlessness is therefore not perfectly free. There is a faint resistance. The astronauts do not feel it directly because the force is weak and acts across the station, but mission controllers can see its result in the changing orbit. Altitude is slowly lost. The station that appears to float so effortlessly inside is being brushed continuously by the last traces of the planet below. Microgravity exists because the ISS and its contents fall together. Orbital decay begins because that shared fall passes through an atmosphere that never reaches a clean ending. And once the floating world inside had shown that gravity was still pulling the station and everyone aboard it toward Earth, the faint atmosphere touching its outer surfaces became the quiet force that prevented the orbit from remaining unchanged forever. From the windows of the International Space Station, Earth's atmosphere appears as a narrow line wrapped around the planet. Blue fades into darker blue, then into black. The transition looks sharp enough to be mistaken for an edge, as though air ends cleanly and space begins on the other side. But the atmosphere has no final wall. It becomes thinner with altitude, molecule by molecule, until ordinary air has turned into a near vacuum. Even hundreds of kilometers above the surface, where the ISS moves, a small number of particles still remain. They are too widely separated to carry sound or support breath. To a human body, the region is space. To a structure moving at nearly 8 kilometers per second, it is not perfectly empty. Every second, the station crosses several kilometers through this extremely thin gas. Hydrogen, helium, oxygen, and other particles strike its forward-facing surfaces at orbital speed. One collision has no meaningful effect. Across the station's large structure, repeated continuously, the collisions create a small resistance. This is atmospheric drag. There is no visible wind outside the windows. No cloud forms around the solar arrays. Nothing bends or shakes in a way the crew could recognize as weather. The force reveals itself through the orbit. A tiny amount of energy is lost. The station's path slowly changes. The effect is weak enough to remain invisible from one moment to the next, but orbital flight lasts far longer than a moment. The ISS travels more than 40,000 kilometers during each circuit of Earth and completes roughly 16 circuits in a day. A faint force acting across that distance cannot be ignored forever. The station is also unusually large for an object in low Earth orbit. Its pressurized modules form only part of the structure. Long trusses support broad solar arrays, radiators, antennas, experiments, and visiting spacecraft. All of these surfaces move through the remaining atmosphere. The exact amount of drag depends partly on how the station is facing. A broad profile meets more particles. A narrower orientation meets fewer. The ISS is always balancing the needs of a living laboratory against the environment slowly reducing its orbital energy. That environment belongs to Earth. The phrase outer space often creates the image of a clean separation from the planet below. Yet low Earth orbit is still inside the outermost reach of the atmosphere. The station has crossed beyond clouds, aircraft, and ordinary weather, but it has not escaped every trace of air. This is one reason its orbit cannot remain permanent without maintenance. The ISS occupies a useful region between those extremes, high enough to provide long periods of microgravity and low enough for crews and supplies to reach it with practical spacecraft. The advantage of being close to Earth is also the source of the slow pull downward. Drag does not simply push the station toward the surface. It removes energy from the forward motion that keeps the station in orbit. The station remains above Earth because it is moving sideways fast enough to keep missing the planet. When resistance reduces that motion, the shape of the orbit begins to change. The path becomes lower. The ISS continues circling Earth, but its average altitude gradually decreases. A lower orbit brings the station into slightly denser atmospheric layers. More particles strike the structure. The drag becomes stronger. Without correction, the process can feed itself, with each loss of height making later losses happen more quickly. As long as the station remains in low Earth orbit, the atmosphere continues taking energy away. The rate is not constant because the upper atmosphere is not constant. It expands and contracts under the influence of the sun. Ultraviolet and X-ray radiation heat the highest layers of Earth's atmosphere. Increased solar activity can add more energy, causing those thin layers to swell outward. More particles in the station's path mean more drag and a faster loss of orbital height. When solar activity becomes quieter, the upper atmosphere can cool and contract. Fewer particles reach the station's altitude, and the orbit may decay more slowly. The sun, therefore, influences the ISS without touching it in any visible way. A disturbance on the sun can change the density of gas around Earth. That change can alter the station's motion days later. The crew may see bright auroras below, while flight controllers see a different consequence in orbital measurements. The station is being slowed by an atmosphere responding to a star more than 100 million kilometers away. The ISS repeatedly crosses from sunlight into Earth's shadow, moving through regions that have been heated differently. Density varies with latitude, season, solar conditions, and local time. The station's path therefore passes through an environment that is always changing, but precise tracking can reveal what human senses cannot. This is why orbital predictions must be updated continually. The ISS is not simply assigned one altitude and left to repeat the same circle forever. Its real path rises and falls slightly. It is affected by Earth's uneven gravity, the movement of onboard systems, docked spacecraft, planned maneuvers, and the atmosphere. Cargo and crew vehicles must know where the station will be when they arrive. The station's path is predictable only because it is constantly measured. The atmosphere ensures that yesterday's prediction slowly becomes less accurate. This creates a quiet contrast between appearance and reality. From Earth, the ISS may cross the night sky with perfect smoothness. Nothing suggests that the orbit is being reshaped by particles too thin to see. Yet every outer surface is meeting the last traces of the atmosphere. The force is too weak to hear and too gentle to feel, but strong enough to move the entire station closer to Earth over time. The solar arrays make this effect especially important. They are essential because the ISS depends on sunlight for electrical power. Life support systems, computers, laboratories, pumps, lighting, cooling, and communication all depend on the energy they produce. Their wide surfaces also increase the area exposed to atmospheric particles. Its size gives it scientific capability and orbital vulnerability at the same time. Controllers can adjust the station's attitude to manage resistance during certain periods, but every change affects something else. It is a connected system that must remain powered, cooled, oriented, inhabited, supplied, and safely positioned while moving through an environment that never becomes perfectly empty. Atmospheric drag near the ISS follows the same broad principle as resistance near the ground, but the result is different. When drag removes energy, the consequence appears as a lower orbit. Its path tightens around Earth. As an uncontrolled object descends into a lower orbit, it may move around Earth faster, even while drag continues removing energy. The atmosphere then removes energy at a greater rate. Orbital decay is therefore not a simple slowing until motion ends. The orbit shrinks until the object reaches air dense enough to make continued circling impossible. At that point, the descent becomes rapid. Heat builds around the object. Structures break apart. The remaining pieces fall more directly through the atmosphere. This is the natural fate of abandoned objects in low Earth orbit. Small satellites, rocket stages, and fragments can remain above Earth for years, but drag slowly changes their paths. The lower they move, the shorter their remaining time becomes. The ISS is subject to the same physics. Its difference is not immunity. Its difference is maintenance. The station's orbit is observed and corrected before decay becomes uncontrollable. Those corrections do not remove the atmosphere or end the drag. They restore some of the energy already lost. After a maneuver raises the station, the gradual descent begins again. This creates a long pattern in the altitude history of the ISS. The path slowly drops. A planned burn lifts it. The path begins dropping once more. The station remains in space because these corrections continue, not because one launch placed it into an orbit that lasts forever. Every reboost is temporary. The atmosphere begins working against it immediately. How quickly the altitude changes depends on conditions that cannot be predicted perfectly. Solar activity may increase. Atmospheric density may rise. A visiting spacecraft can alter the shape and mass of the combined station. Even small differences matter when calculations extend across many orbits. The station therefore exists inside a moving balance rather than a fixed location. It is always falling around Earth. It is also always losing a little of the motion that allows that fall to continue safely. The two processes happen together. Gravity bends the path, the thin atmosphere weakens it. This reveals how close the ISS still is to the world below. The Moon is separated from Earth by hundreds of thousands of kilometers, The station is only a few hundred kilometers above the surface. It remains inside Earth's magnetic field and the outer reach of its atmosphere. Crews can arrive within hours. Emergency vehicles can return them to the ground. The black sky makes the ISS appear far away, but in astronomical terms, it is barely above the planet. Its connection to Earth has never been broken. The visible blue line beneath the station is more than a beautiful boundary. Its faintest particles extend upward until they meet the hull. The atmosphere that protects life near the surface becomes a source of drag at orbital altitude. The same layer that burns many incoming objects during re-entry is already beginning its effect far above the clouds. At 400 kilometers, that effect is gentle. Lower down, it becomes much stronger. Speed makes the thin gas important. If the station were moving slowly through the region, the scattered particles would have little consequence. But the ISS strikes them at orbital velocity for months and years. Time allows an almost non-existent atmosphere to reshape the path of a structure weighing hundreds of tons. A force too small to notice during one orbit becomes kilometers of lost height across a longer period. Nothing dramatic needs to happen. No explosion is required. No large object has to strike the station. It can simply continue crossing the same quiet darkness while its orbit slowly weakens. This is what makes the process slightly unsettling. The view can remain unchanged while the danger grows. Astronauts can continue working, exercising, eating, and sleeping as the station gradually moves lower. Earth still turns beneath the windows. Sunrise still arrives at the horizon. Inside, everything continues floating. Only the measurements reveal that the path is tightening. Ground teams monitor those measurements because the decay cannot be allowed to continue indefinitely. The loss may be slow, but the direction is clear. A lower station meets denser air. Denser air creates stronger drag. Stronger drag lowers the station more quickly. The long, gentle descent would eventually become a much faster one. The station survives because this sequence is interrupted. Energy is returned to the orbit before the remaining atmosphere can take too much away. Engines on attached spacecraft can push the ISS forward, changing its motion and raising its path. Those burns last only a short time compared with the months of gradual decay they are correcting. For a few minutes, the quiet station becomes a powered vehicle again. Then the engines stop, and the slow loss resumes. The ISS has never escaped the atmosphere completely. It has only entered a region where the atmosphere works patiently. Its pull is not felt as weight. Its resistance is not heard as wind. It appears only in the changing numbers describing altitude, velocity, and future position. Those numbers decide how long the station can remain safely above Earth. And once the last traces of Earth's atmosphere had revealed how they were quietly stealing energy from the station's orbit, the slow descent that followed became the reason its altitude could never be left uncorrected for long. The loss does not arrive as one visible drop. The International Space Station can circle Earth again and again while the view outside appears unchanged. Oceans move beneath it, storms turn slowly across the atmosphere, and sunrise returns at the curved horizon. Nothing in those scenes reveals that the path has become slightly lower. A few hundred meters can disappear from the orbit, then more. The station remains far above every mountain, aircraft, and cloud, but the gradual direction is downward. The phrase sounds sudden, yet the real process is patient. The ISS does not stop moving and fall straight toward the surface. It continues traveling around Earth at enormous speed while the shape of its path becomes a little smaller. That change matters because the atmosphere becomes denser as altitude decreases. A lower station meets more particles. More collisions create stronger drag, and stronger drag removes orbital energy more quickly. Under normal operations, the station never reaches the point where this becomes uncontrollable. Its altitude is watched carefully, and the orbit is corrected, before the lower atmosphere can take too much energy away. But the natural process never reverses on its own. Once drag has removed energy, the station cannot recover that energy simply by continuing to orbit. Without propulsion, the average altitude keeps decreasing. The rate of decline is never perfectly constant. Earth's upper atmosphere changes under the influence of the sun. It heats, cools, expands, and contracts, altering the number of particles at the height of the station. During quieter solar conditions, the atmosphere can become thinner around the ISS. Drag weakens, and the orbit decays more slowly. When the sun becomes more active, ultraviolet and X-ray energy heat the outer atmosphere. Those thin layers expand upward, placing more particles in the station's path. The connection stretches across an enormous distance. Activity on the sun changes Earth's atmosphere. The changing atmosphere increases drag, and drag reshapes the station's orbit. A disturbance on a star more than 100 million kilometers away can eventually alter the fuel planning of a spacecraft circling Earth. They continue floating, working, exercising, and sleeping, while the station moves through an atmosphere that has become slightly less empty. Tracking data begins to drift from earlier predictions. The station arrives at a point in its orbit a little earlier or later than expected. Its altitude may be decreasing at a rate that no longer matches the earlier model. This is why the future position of the ISS is calculated repeatedly. The station is not given one path and then left to follow it forever. Radar observations, navigation systems, ground measurements, and atmospheric estimates are combined to update the orbit. Small uncertainties grow with time. A slight error in atmospheric density produces a slight error in drag. That becomes a small difference in velocity, which slowly becomes a larger difference in position after many revolutions around Earth. A cargo vehicle cannot aim directly at the ISS and correct everything during the final minutes. Its approach is built from carefully timed engine burns, each one creating a new orbit that brings it closer to the station later. It influences rendezvous planning, communication passes, Earth observations, debris tracking, and the timing of scientific work. The ISS is always traveling toward a future location. That location has to be known well enough for spacecraft, antennas, cameras, and control teams to meet it. There is a higher part and a lower part, and those points can change separately. Atmospheric drag, Earth's uneven gravity, docking vehicles, and planned maneuvers all shape the path. It is a living path, constantly measured and occasionally reshaped. Even the amount of time required for one orbit changes slightly as altitude changes. A lower path is smaller, allowing the station to circle Earth a little more quickly. That history can be drawn as a line that slowly falls, rises sharply after a reboost, and begins falling again. The station's survival appears as a sequence of recoveries from a descent that never fully stops. Controllers do not always try to hold the ISS at one exact altitude. Sometimes the orbit is allowed to fall for operational reasons. A lower station may be easier for an arriving spacecraft to reach with limited fuel. Fuel availability, visiting missions, debris risks, solar conditions, and future schedules all influence the chosen altitude. Modules were added over many years. Solar arrays, radiators, laboratories, antennas, and external equipment altered its mass and shape. Visiting vehicles arrive and depart, changing the configuration again. Its solar arrays stretch across an enormous area, giving the last traces of the atmosphere more surface to strike. They provide electricity for life support, computers, experiments, lighting, cooling, pumps, and communication. The station cannot simply fold itself into a small shape for the entire mission. Its scientific value requires the same broad structure that makes atmospheric drag more important. The station has to remain a functioning laboratory, while its orbit is slowly being eroded. Solar activity can make that erosion far less predictable. The Sun follows long cycles, but individual periods of activity can rise and fall on shorter timescales. The upper atmosphere may expand more than expected, increasing drag on many objects in low Earth orbit. The station does not need to be struck by a solar eruption for the Sun to affect it. Heating the atmosphere below is enough. The difference becomes lost altitude, and lost altitude places the station inside slightly stronger drag. The process remains gentle, only while the orbit stays high enough for the gas to remain extremely thin. If all corrections stopped, the early stage might look completely normal. The station could remain powered for a time. Computers might continue sending data. Solar arrays could still turn toward the Sun, and the ISS would continue crossing the night sky as a bright moving point. The station would circle Earth on a slightly smaller path while the resistance increased around it. The ending would be built from thousands of small losses. As altitude decreased, the atmosphere would become less forgiving. Particles would strike the structure more frequently. Orbital energy would be removed faster. The time between meaningful changes would shrink. Eventually, the station would pass through air dense enough that stable orbital flight could no longer continue. At that stage, the ISS would still be moving at many kilometers per second. The atmosphere would compress and heat around the leading surfaces. Solar arrays and exposed equipment would experience forces they were never designed to survive. The station would not return as one complete structure. External components would tear away. Connections could fail. Modules and trusses would begin breaking apart, while the remaining pieces continued moving across the atmosphere at extreme speed. An uncontrolled return would be difficult to predict far in advance, because tiny differences in drag would grow rapidly during the final orbits. A shift of only a few minutes could move the re-entry point across thousands of kilometers of Earth. This is why the station cannot simply be abandoned and allowed to choose its own ending. Most of the planet is ocean, but the ISS also passes above populated land. Even a small risk from surviving debris has to be reduced as much as possible. The natural decay of the orbit creates a responsibility long before the final mission ends. The station must be maintained while it is operating, and its eventual return must be guided. The same physics responsible for that future return is already acting today. At the present altitude, the decay is slow enough to measure and correct. Each reboost interrupts the descent before it reaches the more dangerous part of the atmosphere. The maneuver restores orbital energy. It pushes the station forward, changing the curve of its path so that the ISS rises toward a higher altitude. A forward burn increases the station's speed at one point, and the new motion carries it toward a higher point on the opposite side of the planet. This is orbital motion again behaving differently from ordinary movement on the ground. The correction is brief. Compared with the descent, it reverses. During that short period, engines return energy that the atmosphere removed almost invisibly across thousands of orbits. Loose objects that were floating freely can drift toward one side of the module. The sensation is weak, but it reveals that the station is no longer in perfect shared freefall during the burn. When the engines stop, the ISS returns to coasting. The new orbit is higher, but the atmosphere immediately begins taking energy from it again. This is why the station has remained above Earth for decades. It survived by having the lost energy replaced again and again. Fuel, spacecraft, calculations, and people on the ground keep the balance from moving too far downward. Without that work, the ISS would not fall immediately. Its existing speed would carry it around Earth many more times. The descent could take months or longer, depending on altitude and solar conditions. But the outcome would already be moving in one direction. Each completed orbit would leave slightly less orbit remaining. The black sky outside would look unchanged, while the blue atmosphere below became physically closer. The station survives because humans act while the danger is still invisible. They respond to a changing altitude before astronauts can feel the change. They use models to prevent an event that would otherwise happen naturally. This is one of the deeper truths of life aboard the ISS. The station looks stable because instability is being managed constantly. Its continued orbit depends on people noticing small changes early enough to correct them. A slow pressure leak, a rising temperature, an approaching fragment of debris, or a loss of orbital height may begin as a measurement long before becoming an emergency. Safety comes from understanding what the measurements will become. Orbital decay is especially deceptive because nothing inside needs to stop. The station can feel completely secure, while the path around the planet becomes slightly lower. Every object in low Earth orbit faces the same broad future. Some satellites are designed to descend naturally after their missions. Others use engines to remain aloft. Objects at higher altitudes may survive far longer because the atmosphere is thinner. The ISS is simply the largest inhabited example of this balance. It is a repeated decision to replace what Earth's atmosphere has taken. That decision needs a source of thrust. Major reboosts have often depended on spacecraft attached to the station. Cargo vehicles arrive carrying supplies and experiments, but some also bring engines and propellant capable of moving the entire ISS. A comparatively small spacecraft docks with a structure weighing hundreds of tons and becomes the source of force for both. Direction, duration, timing, crew activities, solar array positions, visiting traffic, and the station's structural limits all matter. The correction must be gentle enough for the structure and precise enough for future operations. For a short time, engines at one part of the station push the laboratories, sleeping areas, solar arrays, crew, air-water equipment, and docked vehicles together. The entire structure responds as one spacecraft. Then, the burn ends. The ISS returns to silent orbital flight, a little higher above Earth than before. The atmosphere begins its patient work again. Drag lowers the orbit. Engines restore it. The principle is simple, but every correction depends on fuel, navigation, communication, hardware, and people spread across control rooms on Earth. The station remains above the planet because that chain continues to function. And once the slow decay of the orbit had shown that the station's fall could only be delayed by returning the energy taken by the atmosphere, the brief engine burns that lift the entire structure became the hidden reason it continued circling safely above Earth. Gravity bends its path around Earth, while the momentum gained long ago carries it through orbit after orbit. Inside, the crew floats in the familiar calm of freefall. Outside, the solar arrays turn toward the sun, and the station crosses the darkness with no visible sign that its altitude is slowly being spent. The burn may last only a few minutes, yet those minutes can replace orbital energy that the upper atmosphere removed across weeks or months. A vehicle built to carry cargo becomes the engine of a structure weighing hundreds of tons. The word sounds as though the station is being pushed straight upward, but orbital motion does not work that way. The engines normally add speed in the direction the ISS is already traveling. That extra forward motion changes the shape of the orbit. At the moment of the burn, the station begins moving slightly faster. Gravity still pulls toward Earth, but the new path carries the ISS toward a higher point on the opposite side of the planet. If only one part of the orbit needs to be raised, a single burn may be enough. If controllers want a more even path, another maneuver can adjust the opposite side later. Every reboost is therefore designed around a specific future orbit, not simply a desire to move farther from the surface. They know its altitude, speed, orientation, mass, and the positions of the docked vehicles. They estimate atmospheric drag, solar activity, visiting missions, debris risks, and the orbital path needed in the days ahead. The ISS already moves at close to 8 kilometers per second. A reboost may alter that speed by only a few meters per second, or less. Across an entire orbit, it is enough to lift the path by hundreds of meters or several kilometers. The station does not need to be pushed all the way to the higher altitude. It only needs the correct change in speed at the correct point in its path. The engines used for these burns have often belonged to Russian Progress cargo spacecraft docked to the station. Progress vehicles arrive carrying supplies, equipment, water, fuel, and other materials, but while attached, they can also provide propulsion for the combined complex. Northrop Grumman's Cygnus cargo spacecraft has performed station reboosts as well. SpaceX Dragon has also demonstrated and used reboost capability, giving the program another way to add energy to the orbit. Once docked, both spacecraft become one connected system. The thrust produced at one end passes through docking mechanisms, modules, trusses, and structural connections until the full complex begins accelerating together. The ISS was assembled from many components launched over decades. Long trusses support solar arrays and radiators. Modules extend in several directions. Docked vehicles add mass at different ports. Controllers consider how the station will flex during the burn, how propellant may move inside tanks, how solar arrays should be positioned, and whether sensitive experiments need protection from vibration. During ordinary orbital flight, the station and everything within it fall together. No surface needs to support a loose object, so the object floats. When engines begin pushing the ISS, the station accelerates around the object. A pen, camera, or droplet of water may drift slowly toward one side of the cabin. When the burn ends, the temporary direction disappears. The ISS returns to coasting, and the cabin becomes weightless again. The result may be described through 2 points: the highest part of the orbit and the lowest. Engineers often refer to them as apogee and perigee. A burn can raise one more than the other, depending on where it occurs and how it is directed. This matters because the station does not circle Earth at one perfectly fixed height. Its orbit is slightly stretched, and both ends must remain within an acceptable range. Reboosts are often timed to prepare for arriving spacecraft. A cargo or crew vehicle launches into its own orbit and gradually adjusts its path to meet the ISS. The station must be in the expected place when that meeting occurs. Changing its altitude changes how long one orbit takes and where the station will be hours or days later. A correctly planned burn can place the station into the right relationship with the launch site and the arriving vehicle. The ISS cannot be raised whenever someone notices that its altitude has fallen. The maneuver has to fit between other operations. A spacecraft may be preparing to depart. Another may be approaching. Astronauts may be using equipment that cannot tolerate unnecessary vibration. Solar arrays may need to be repositioned. The orbit drifts lower slowly, then rises during a short burn. The descent begins again almost immediately, but from a higher starting point. How much time depends on how high the new path reaches and how the atmosphere behaves afterward. During quiet solar conditions, the reboost may protect the station's altitude for longer. If the sun heats and expands the upper atmosphere, stronger drag can spend the restored energy sooner. A reboost can also be used for reasons more urgent than ordinary orbital maintenance. Low Earth orbit contains fragments of old spacecraft, rocket stages, and satellites. These objects travel at speeds that can make even a small piece dangerous. Tracking networks watch their paths and estimate whether any will pass too close to the ISS. If the predicted risk becomes unacceptable, the station can perform a debris avoidance maneuver. The engines raise or lower the orbit just enough to move the ISS away from the future meeting point. A brief burn performed hours before the predicted encounter can create kilometers of separation later. The same principle that restores altitude can therefore protect the crew from a collision. Atmospheric drag continues, debris continues moving, and visiting spacecraft continued, depending on a predictable orbit. The ISS needs docked vehicles, working engines, usable propellant, control software, navigation, communication, and teams prepared to command them. The station's height is maintained by an international chain of systems, rather than one permanent engine hidden somewhere inside. For much of its history, the Russian Segment and Progress spacecraft supplied the main propulsion used for reboosts and larger attitude maneuvers. American control moment gyroscopes usually manage the station's orientation without burning propellant. But gyroscopes cannot replace the orbital energy lost to drag. The addition of Cygnus and Dragon reboost capability increases the number of vehicles that can help, but every system has different limits: engines, docking positions, and amounts of available fuel. The station's attitude must be prepared before thrust begins. Its orientation determines the direction in which the engines will push and how forces travel through the structure. Gyroscopes may control the station during normal flight, while thrusters help during more dynamic operations. Controllers in different countries coordinate commands and monitor their own parts of the complex. During the burn, teams watch engine performance, acceleration, station attitude, structural response, and navigation data. The real change in velocity may differ slightly from the planned value because engines and propellant systems are physical machines, not perfect mathematical objects. Future predictions are updated. Arriving spacecraft receive revised information. The station settles into its new path. To someone standing outside beneath the night sky, none of this is visible. The ISS still appears as the same bright point crossing above the horizon. A reboost does not suddenly make it look higher. The difference is too small compared with the full distance from the observer. Yet those hidden kilometers decide how strongly the atmosphere will touch the station during the coming weeks. A slightly higher orbit means fewer particles. Fewer collisions mean less drag. Less drag means more time before another burn is required. The maneuver changes the pace of the station's descent without ending it. Fuel makes this cycle possible, and fuel is limited. A cargo spacecraft can carry only a certain amount of propellant. Some must be reserved for its own approach, docking, attitude control, departure, and disposal. The amount available for reboost depends on the design of the vehicle and the needs of the mission. Using fuel to raise the ISS means that fuel cannot be used for something else. Every burn becomes part of a long resource calculation. The station does not need one final burst powerful enough to remain in orbit forever. No practical burn could create that result while keeping the ISS in its present operating region. It needs repeated, controlled additions of energy for as long as humans want it to remain there. This creates a quiet dependence on visiting spacecraft. Food and experiments are visible reasons for cargo missions, but propulsion can be just as important. A vehicle arriving at the station brings not only material, but another period during which the orbit can be managed. When it departs, the propulsion arrangement changes again. Controllers must always know which engines are available and how long their propellant will last. The ISS looks independent because it moves alone above Earth. In reality, its orbit depends on a continuing connection to launch sites, factories, tracking stations, control rooms, and people on the surface. Rocket fuel is created on Earth. Spacecraft carry it upward. Docking systems connect it to the station. Commands from the ground release it through engines. The orbit rises. A small amount of Earth is burned to keep the station away from Earth. The process repeats because the atmosphere never stops reaching upward. There is something almost circular in this arrangement. The ISS exists to allow humans to live and work beyond the atmosphere. Yet remaining there requires a steady supply of machines and fuel from the world below. The station is close enough to be visited, supplied, and raised. It is also close enough to be slowed. Its useful orbit and its vulnerability come from the same distance. Moving the ISS much higher might appear to solve the problem. The atmosphere would become thinner, drag would weaken, and reboosts could become less frequent. A station placed far above low Earth orbit might seem safer from the slow decay that constantly threatens the present path. But altitude creates costs, as well as protection. Every spacecraft visiting the ISS would need additional energy to reach it. Travel times and mission designs could change. Radiation exposure could increase as the station moved farther through regions of Earth's magnetic environment. Emergency return would become more difficult. The orbit that requires repeated maintenance is also the orbit that keeps the station accessible. The ISS was never designed only to stay aloft for the greatest possible time. It was designed to be used. Crews had to reach it. Cargo had to arrive regularly. Large modules had to be assembled across many launches. Space shuttles, Soyuz spacecraft, Progress vehicles, Cygnus, Dragon, and other mission systems were built around the practical demands of low Earth orbit. The station's location is therefore a compromise written into its entire structure. It is high enough for continuous freefall, low enough for repeated human access, far enough above the dense atmosphere to remain in orbit, close enough to the remaining atmosphere that engines must keep rescuing that orbit. Each reboost preserves the compromise, rather than escaping it. The brief burn raises the station, but not so far that the mission becomes something different. It returns the ISS to the narrow region where science, crews, cargo, communication, emergency planning, and orbital life can continue together. Then the engines become silent. The station resumes its fall around Earth. The atmosphere begins removing energy again, particle by particle, orbit by orbit. Another correction will eventually be needed. And once the reboosts had revealed that the station survived through repeated, carefully measured returns of orbital energy, the deeper question became why it had been placed low enough to need this constant rescue instead of being sent into a quieter orbit much farther from Earth. The atmosphere becomes thinner with altitude. Drag weakens. A spacecraft can remain aloft for longer without repeatedly replacing the energy lost to the air below. The ISS was not designed as an object to be launched once and left untouched. It was designed as a place where people would live, where cargo would arrive, where laboratories would be repaired, and where hundreds of separate parts would be assembled across many years. The station usually circles only a few hundred kilometers above the surface. In astronomical terms, this distance is almost nothing. The Moon is roughly 1,000 times farther away, and even many satellites orbit far above the ISS. Its closeness is what makes regular human access possible. A crew vehicle must climb out of the thick atmosphere, gain orbital speed, match the station's inclined path around Earth, and arrive with enough fuel for docking and a safe return. Moving the destination much higher would demand more from the launch vehicle, more from the spacecraft, or both. The difference is not only the fuel needed to rise farther from Earth. A vehicle must also enter the correct orbit and match the motion of the station. Higher paths have different speeds and longer orbital periods, changing the entire journey. A very large increase could require new spacecraft, new rockets, new heat shields, new procedures, and new emergency plans. Space shuttles carried large modules, truss sections, solar arrays, laboratories, supplies, and construction crews. Russian rockets launched other major components. Later, vehicles were designed to continue the flow of people and cargo after assembly was complete. The ISS could not simply be moved far higher after construction without changing the system that supports it. The station requires food, water, clothing, replacement parts, experiments, medical supplies, and equipment. Waste must be removed. Crews must rotate. Vehicles must remain available for emergency return. If a serious medical problem develops, the return vehicle can separate and bring the astronauts back through the atmosphere. A returning spacecraft might enter the atmosphere with greater speed, requiring stronger protection. An emergency that is manageable in low Earth orbit could become more difficult when the crew is farther away. The ISS was meant to be humanity's permanent workplace in space, but not a place completely isolated from the planet. Modules arrived separately. Crews connected cables, installed equipment, unfolded solar arrays, joined trusses, and prepared docking ports for future missions. Each launch had to carry enough mass to orbit, while leaving the spacecraft capable of meeting the station. Placing the assembly site much higher would have reduced the amount of useful hardware each mission could deliver, or demanded more powerful launches. Low orbit made the station vulnerable to drag, but it made the station possible. The ISS remains within much of Earth's magnetic protection, though the crew still receives far more radiation than people on the surface. Energetic particles from the sun and from distant cosmic sources can pass through the station. The orbit also crosses the South Atlantic anomaly, where part of Earth's radiation environment reaches closer to the planet. Earth is surrounded by regions of trapped energetic particles known as the Van Allen radiation belts. Their exact shape and intensity change, but the stronger parts begin above the normal orbit of the station. A station placed much farther away could spend more time in a harsher radiation environment. The walls of the ISS provide some protection, but they were not designed as the heavy shielding of a deep space shelter. A higher orbit could reduce atmospheric drag while creating a larger problem from radiation. The ISS exists where these disadvantages remain manageable together. That distinction matters because engineering rarely finds a place where every problem disappears. It finds a region where several problems can be controlled at the same time. Radiation can be monitored and reduced through shielding, mission limits, and operational planning. The orbit asks for constant maintenance, but the maintenance is possible. A higher orbit might ask for less fuel to fight drag while demanding far more energy from every visiting mission. Across decades of operation, the total balance can favor staying low and performing repeated reboosts. Cameras and instruments pass above large parts of the inhabited world. The orbit's inclination carries the ISS across a wide range of latitudes, while Earth rotates beneath it. From this path, astronauts can photograph storms, wildfires, coastlines, cities, glaciers, volcanoes, and changes across the atmosphere. The station can cross from one horizon to the other in minutes, watching the surface change beneath it. A station can experience continuous microgravity while remaining only a few hundred kilometers above the surface. Low Earth orbit extends much farther, and every altitude has its own population of satellites, debris, radiation conditions, and operational limits. Moving the station upward could place it closer to other useful orbital regions, or increase the time that debris remains aloft. The station's enormous size would remain a concern. Its solar arrays and trusses create a wide target. Even a small fragment moving at orbital speed can carry enough energy to damage a surface, puncture equipment, or threaten a pressurized module. The ISS already uses shielding against smaller impacts, and larger tracked objects can lead to avoidance maneuvers. Changing altitude would not remove this danger. It would move the station into a different part of the same crowded environment. The idea of raising the completed ISS far above its current orbit has been studied in connection with the end of its life. In theory, a high enough orbit could preserve the station for longer, reducing the need for a controlled return. In practice, the maneuver would be far more demanding than an ordinary reboost. A normal reboost may raise the path by a few kilometers. Preserving the station would require a much larger change, enough to move hundreds of tons of structure into a region where it would remain safely away from commonly used orbits for a very long time. The ISS was not built with a large propulsion system capable of performing such a move alone. Docked cargo vehicles can maintain the present orbit, but maintaining and dramatically relocating are different tasks. A vehicle powerful enough to raise the full station much farther would need large amounts of propellant and a way to apply thrust without overstressing the structure. The station is wide, flexible, and assembled from many connected parts. It cannot be treated like one compact satellite. Long engine burns could create structural loads, vibrations, and control problems beyond those of routine reboosts. The higher destination would also have to be chosen carefully. It could not interfere with active spacecraft or leave the ISS drifting through a region where later collisions might create more debris. Even if the move succeeded, the station would not become a useful museum that astronauts could visit easily. Its systems would age, power equipment would fail, the interior would slowly become uninhabitable without maintenance. Radiation, temperature cycles, micrometeoroids, and material degradation would continue. A preserved orbit would save the structure from atmospheric destruction while placing it beyond the practical reach of the vehicles designed to support it. The ISS would remain above Earth, but its purpose would be gone. This reveals the difference between keeping an object in space and keeping a station alive. An abandoned satellite can continue orbiting after its mission ends. A human laboratory needs air, power, cooling, communication, repairs, propulsion, supplies, and people. Its orbit is only one part of survival. Raising the station far higher would solve none of the internal needs. It could make many of them harder to meet. The present altitude was chosen because the ISS is not merely an object. It is a destination. A destination must remain connected to the travelers who use it. Every crew launch, cargo flight, docking, reboost, and return proves that connection is still working. The atmosphere takes energy from the orbit, but Earth provides the people and machines that restore it. The same planet both pulls the station downward and keeps it alive. This relationship explains why the ISS was never meant to escape Earth completely. It was built to test how humans live in space while remaining close enough for support. Experiments aboard the station prepare for missions that will travel farther, where immediate return and regular cargo deliveries may not be possible. The ISS allows those risks to be studied in a place where help is still near. Crews experience months of microgravity, radiation, confinement, maintenance, and isolation. But they do so within a narrow corridor of access above the planet. Moving much higher would begin changing the station from a low Earth orbit laboratory into a different kind of mission. Its systems, vehicles, and safety plans were not designed for that transformation. The low orbit is therefore not an accident left over from launch. It is part of the station's identity. The height supports the way it was assembled. It supports the spacecraft that visit it. It supports the ability of astronauts to return. It supports Earth observation and communication. It limits, though does not remove, exposure to the harsher radiation environment farther out. In exchange, the station accepts drag. It accepts reboosts. It accepts a lifetime that cannot continue forever. The compromise has worked for decades, because each weakness has a response. Atmospheric drag is answered with propulsion. Radiation is answered with monitoring, shielding, and mission planning. Equipment failure is answered with repairs and replacement parts. Crew needs are answered with cargo missions. Medical risk is answered partly by keeping a return vehicle docked. No response is perfect, but together, they allow the station to remain inhabited. A much higher orbit could weaken one problem while breaking several of these answers. This is why the ISS still circles close enough for people on the ground to watch it pass overhead. Its bright movement through the night sky comes from sunlight reflecting off a structure that has not gone far from home. The blackness surrounding it creates an image of deep space. But Earth remains only minutes away by orbital motion and hours away by spacecraft. The station lives at the edge of the planet's atmosphere, not at the edge of Earth's influence. That closeness makes the orbit temporary, It also makes the mission sustainable. For every kilometer of altitude that the atmosphere slowly removes, the station receives another period of access, support, and protection that a distant orbit could not provide as easily. The cost is paid through fuel and constant attention. The reward is a laboratory that can be inhabited year after year. Yet remaining low brings another danger that altitude alone cannot solve. The station shares this region with thousands of active satellites, old spacecraft, rocket bodies, and fragments produced by earlier collisions and breakups. Some are tracked from Earth. Many smaller pieces cannot be followed continuously. All of them move through orbit at speeds that turn even a tiny object into a potential threat. The ISS cannot choose its altitude only by looking at atmospheric drag, radiation, and access. It must also move through an environment already occupied by the remains of human activity. The same low orbit that keeps the station connected to Earth places it inside a crowded, changing field of objects. Every future position must be predicted, not only to guide arriving spacecraft, but to make sure nothing else will be there at the same time. And once the station's low altitude had revealed itself as the compromise that made assembly, supply, research, and emergency return possible, the crowded, orbital environment surrounding that useful path became the next quiet danger that had to be watched without pause. Earth fills much of the view below, while the rest appears black and still. No traffic lanes are visible. No warning lights mark the paths of nearby satellites. Most objects are too small, too dark, or too distant to be seen by the crew. It contains working satellites, abandoned spacecraft, spent rocket stages, fragments from collisions, pieces released during breakups, and smaller objects created by decades of activity above the planet. At those speeds, size becomes misleading. A fragment that would seem harmless on the ground can carry enormous energy in orbit. A small bolt, a chip of metal, or a piece of damaged satellite does not need to be heavy to become dangerous. It only needs to meet the station at a high relative speed. The ISS cannot slow down and wait for the object to pass. Both are following orbital paths around Earth. A collision may be predicted hours or days before it happens, but the moment itself could last less than a second. Only calculations reveal that two paths could cross at the same place and almost the same time. Tracking networks on Earth watch thousands of objects large enough to be followed reliably. Radars send signals upward and measure the returning echoes. Optical telescopes record small points of reflected sunlight. Repeated observations allow analysts to estimate each object's orbit and predict where it will move. Every orbit changes. Atmospheric drag alters low objects. Solar activity changes the upper atmosphere. Gravity produces smaller disturbances. Satellites maneuver. Fragments tumble and react differently to sunlight and air. A prediction that is accurate today becomes less certain with time. Computers project the motion forward and search for close approaches. Most predicted encounters do not become emergencies. The objects pass at safe distances, or later measurements show that the early estimate was too uncertain. But some encounters remain close enough to require action. Move the station too often, and fuel is wasted. Scientific work is interrupted. Docking plans may need to change. The new orbit can create different conjunctions later. Controllers must judge both distance and uncertainty. A predicted miss of several kilometers may sound safe, but the estimated position of a small object can include a wide region of uncertainty. The real fragment could pass above, below, ahead, behind, or directly through the station's path. It is how certain anyone can be about that expectation. When the risk becomes too high, the ISS can perform a debris avoidance maneuver. The station does not turn away at the last moment like an aircraft avoiding another plane. Orbital motion requires earlier action. A short engine burn changes the ISS's speed by a small amount. That alters the shape and timing of its orbit. Hours later, the station arrives at the crossing point sooner, later, higher, or lower than it otherwise would have. A maneuver that produces only a small change in velocity can create kilometers of separation after enough time has passed. Sometimes the station is raised slightly. Sometimes the timing changes more than the altitude. The exact choice depends on the encounter, the engines available, visiting spacecraft, fuel, station orientation, and future mission plans. Avoidance is another reason the orbit can never be treated as permanent. Even if atmospheric drag vanished, the station might still need to move because the path is shared with too many other objects. If a warning arrives too late for a safe avoidance burn, the crew may move into the docked spacecraft that would carry them home during an emergency. Hatches can be prepared, and the station can be placed in a safer configuration while teams continue tracking the object. They wait inside the return vehicles so that if the station is seriously damaged, they have a better chance of separating quickly. But for a short period, the possibility exists that an invisible object could end a mission lasting decades. Danger can pass within kilometers while remaining completely unseen. Larger objects can be tracked, but smaller debris creates a different problem. Millions of fragments may be too small for continuous observation from the ground. Some are smaller than a coin. Others may be no larger than a grain of paint. At orbital speed, even these can damage exposed surfaces. The ISS carries evidence of such impacts. Windows and external equipment can develop small pits and marks. Protective layers may be struck. Samples returned from outside can show tiny scars from an environment that appeared empty. Its pressurized modules use protective systems that can break apart and spread the energy of smaller incoming particles before they reach the pressure wall. An outer layer causes the particle to fragment, and deeper layers absorb the wider cloud of material. It improves the chance that a small impact remains a damaged surface rather than a punctured cabin. Different parts of the ISS receive different levels of protection. The forward-facing side meets more particles because the station is moving into them, while other surfaces can still be struck by objects on crossing or opposing paths. Shielding everything heavily would add enormous mass and could prevent systems from functioning. The design therefore accepts that some surfaces will remain vulnerable. Survival depends on layers of defense rather than one perfect barrier. The source of the debris makes the problem more difficult. A satellite can break apart because of a collision, an explosion, a failed battery, or remaining fuel. One object becomes hundreds or thousands of fragments, each entering a slightly different orbit. Across enough time, this can become a chain in which the growing population of fragments makes certain orbital regions increasingly dangerous. Low Earth orbit is enormous, but useful paths are concentrated. Earth observation satellites, communication systems, scientific missions, crewed vehicles and stations often need similar altitude ranges. A fragment can circle Earth thousands of times, repeatedly passing through regions used by other spacecraft. Atmospheric drag eventually removes many objects from lower orbits, but the cleanup may take years. Higher up, debris can remain for decades or centuries. Drag slowly lowers the station, yet it also prevents part of the debris population from remaining forever. A higher orbit might reduce the need for reboosts while allowing dangerous fragments to survive much longer. New satellites are launched regularly. Some enter very low paths and re-enter quickly. Others remain for years. Large groups of satellites can occupy similar altitude ranges, increasing the number of objects that must be tracked and coordinated. The future safety of the ISS depends partly on decisions made by missions that have nothing to do with the station. Space has no physical border separating one nation's orbit from another. The environment demands cooperation. Tracking data is shared. Warnings move between agencies. Operators coordinate maneuvers. Launch plans are compared. The station can avoid an object only if its path is understood early enough. Most of this work remains invisible. A successful avoidance maneuver produces no dramatic image. Nothing explodes. The ISS simply continues its orbit. Success looks like an event that never happened. This makes orbital safety easy to underestimate. The bright point crossing the night sky may look alone, but a moving catalogue of human-made material is constantly compared with its future path. Every reboost changes that comparison. Every docked vehicle changes the available propulsion. Every new satellite changes the wider environment. The orbit must be watched as a living system. Natural particles add another layer. Micrometeoroids move through space independently of human activity. Many are tiny remains from comets or collisions between natural bodies. Most are too small to threaten the station seriously, but some can strike with great speed. The ISS therefore faces both the ancient environment of the solar system and the debris created during the brief age of spaceflight. A particle may have traveled for millions of years. A fragment from a satellite may have been created months earlier. Both can arrive without any visible warning. Human debris can at least be reduced. Spacecraft can be designed to release fewer objects. Fuel tanks and batteries can be made safer after missions end. Satellites can be guided into the atmosphere or moved into disposal orbits. Better tracking can reduce uncertainty. International rules can lower the chance of intentional or accidental fragmentation. These actions cannot remove everything already present, but they can slow the growth of the problem. The ISS itself must also avoid becoming debris. Its modules, solar arrays, trusses, and equipment cannot simply be abandoned in a decaying orbit after the crew leaves. An uncontrolled breakup could scatter material across low Earth orbit before the largest pieces reach the atmosphere. The station's eventual disposal therefore matters not only to people on the ground, but to every spacecraft that will use the region afterward. For now, the ISS remains active and controlled. Its position is tracked. Its orbit is corrected. Docked vehicles stand ready. The crew follows procedures built from years of experience. This control separates the station from the uncontrolled objects around it. An abandoned satellite cannot move when debris approaches. A spent rocket stage cannot raise its orbit. A dead spacecraft cannot answer commands. The ISS can still respond, but response depends on power, communication, propulsion, and people. If those connections ended, the station would not become safe simply because no crew remained aboard. It would become another large object, moving through the same crowded environment. Its orbit would decay. Its position would grow harder to predict. No engines would move it away from debris. No team would plan its future path. The controlled laboratory would begin turning into the most massive, uncontrolled spacecraft ever left in low Earth orbit. This is why orbital maintenance and debris monitoring cannot be separated. Reboosts keep the station high enough to operate. Avoidance burns keep it away from dangerous encounters. Tracking tells controllers when either action is needed. The station remains above Earth because all three continue together. The danger is not only that gravity and drag pull it downward, it is that the orbit around it is filled with other paths, each carrying an object that may arrive at the wrong place at the wrong time. A collision large enough to damage the station could change its orbit, release more debris, destroy systems, or force the crew to leave. The event would be sudden, but the risk exists every day in the background. This creates a quiet tension beneath the routine aboard the ISS. Astronauts conduct experiments, prepare food, exercise, repair equipment, and speak with families on Earth. Outside, the station passes through a region mapped by radar and watched from control rooms. Warnings appear. Probabilities are updated. Most fade away. A few become maneuvers. The station survives through attention to dangers that rarely become visible. That attention cannot continue forever. The ISS was designed for a long mission, not an endless one. Hardware ages. repairs become harder. Vehicles, partnerships, and budgets change. Eventually, crews will leave, and the station will stop functioning as a permanent laboratory. At that moment, the orbital problem will not disappear. It will become more serious. A structure this large cannot be allowed to drift without a plan. The atmosphere will continue lowering it. Debris will continue crossing its path. Every system needed for control will have a limited lifetime. The question will no longer be how to avoid one dangerous object or restore a few lost kilometers. It will be what happens when the reboosts, tracking decisions, and careful corrections finally stop. And once the crowded orbit had revealed that the station survived only because its position, propulsion, and surrounding debris were watched continuously, the thought of what would happen if that control finally stopped became impossible to avoid. The International Space Station would continue circling Earth at nearly the same speed, crossing oceans and continents while sunlight moved across its solar arrays. From the ground, it would still appear as a bright point traveling smoothly through the night sky. Its orbit would not collapse the moment the final command was sent or the final engine fell silent. Gravity would keep bending the path around Earth, and the thin atmosphere would keep removing energy as it had done during every earlier year of the mission. The only difference would be that no later burn would return what the atmosphere had taken. The first changes would appear in measurements rather than through the windows as the average altitude began drifting downward. The highest and lowest parts of the orbit would change. Predictions made weeks earlier would slowly lose accuracy as atmospheric density, solar activity, and the station's changing orientation altered the amount of drag. From a typical operating altitude, natural atmospheric decay could take roughly a year or two to bring the station back into the atmosphere, although the real timing would depend strongly on the sun and on conditions no one could forecast perfectly so far in advance. At first, a small error in predicted drag might shift the station's position by only a little. After thousands of revolutions, that difference could become large enough to move the final re-entry path across oceans and continents. A change of only a few minutes in the final arrival could move the breakup region by thousands of kilometers. This is why an uncontrolled re-entry cannot be aimed toward one safe place far in advance. If the crew were still aboard when reboost capability was lost, the first response would not be to wait for the station to fall. Crew vehicles are kept docked partly because the station is not a refuge that can be occupied after every major system fails. They are lifeboats as well as transport. A serious loss of propulsion would be studied from the ground. Engineers would ask whether another docked vehicle could take over, whether a new spacecraft could be launched, and whether the orbit remained high enough to allow time for recovery. A single engine problem would not end the station. The ISS has used different visiting spacecraft and propulsion systems across its history, and failures can sometimes be isolated or replaced. Power and communication might continue for a time, while attitude control equipment held the station in a planned orientation and ground controllers kept sending commands. But the station would no longer be preserved as a home, and every remaining capability would depend on propellant, electricity, and aging hardware that could not last forever. It would pass through a period between operation and abandonment, still functioning in limited ways, while its future became steadily harder to change. Controllers might use attitude changes to extend the remaining time, much as earlier space stations used orientation to reduce atmospheric resistance. But no orientation could restore the energy already lost. As the orbit lowered, the atmosphere would gradually become less like an almost perfect vacuum. The difference would still be invisible to any camera outside. There would be no cloud around the modules, and no ordinary wind moving across the solar arrays. The ISS would circle Earth faster, in the sense that it completed a smaller orbit in less time, even while atmospheric drag continued carrying it toward destruction. The station would remain recognizably in orbit, but the time left would be decreasing at a faster rate. What had once been a slow, manageable decline would become a process that no longer offered long pauses between corrections. The ISS would be entering the most crowded and uncertain part of its final life, at the same time that its ability to respond was disappearing. Its orbit would continue crossing the paths of satellites and debris, while becoming less predictable. The ISS is far larger than most spacecraft in low Earth orbit. A collision could release fragments long before the atmosphere removed the main structure. As altitude fell, atmospheric drag would eventually help clear those fragments as well, but not immediately. Some could enter different paths and remain above Earth after the station itself was gone. Eventually, the lowest point of the orbit would enter air dense enough to produce much stronger resistance. A process that had unfolded across years would begin accelerating across days, then hours. At this point, the remaining path would become extremely sensitive to small conditions. Density changes between day and night, the station's exact orientation, the timing of solar activity, and the way its large, flexible structure responded to increasing forces. Any of them could influence where the final breakup occurred. The ISS was built for vacuum and microgravity, not for controlled flight inside an atmosphere. Its shape is wide and delicate, with long solar arrays extending from the central truss and radiators. Antennas, experiments, robotic equipment, and docked vehicles forming a complex outline, rather than one protected re-entry capsule. No heat shield surrounds the full structure, and no aerodynamic shape is designed to guide it through the sky. As meaningful re-entry began, the outer components would meet rising pressure and heat, while the station was still moving at orbital speed. The leading surfaces would experience the greatest stress. Solar arrays could bend, tear, or separate. External equipment could break free, and the truss would flex under forces far beyond those of a normal reboost. Connections designed to hold modules together in orbit would begin carrying loads from an atmosphere becoming denser every second. The station would not fall as one recognizable object all the way to the surface. It would come apart. Heating around the structure would become intense as the air ahead was compressed and disturbed. Materials would melt, burn, and fracture. Released pieces would follow their own paths, creating a long trail rather than one compact impact point. Lighter components would lose speed more quickly. Dense machinery, tanks, structural joints, and other heavy parts could survive longer. Much of the ISS would be destroyed high above Earth, but not everything could be guaranteed to disappear, because the station's mass is simply too great. Some components are too dense and too resistant to heating to assume that the atmosphere would consume them completely. This is the central problem of an uncontrolled return. The risk is not that the entire station would land intact on a city, because that could not happen. The danger comes from a smaller fraction of the original structure, surviving as scattered debris across a long region of Earth. Most possible paths would cross ocean, because oceans cover most of the planet. But probability is not control. The ISS travels over broad areas of inhabited land during ordinary operation. Without a targeted maneuver, no one could choose which final orbit became the last. Predictions would improve only as the station moved closer to re-entry. Days before the fall, the possible region might still circle much of Earth. Hours before, the window would narrow. Only near the end would analysts know the likely track with useful precision, and by then, there might be no functioning propulsion left to change it. The station would have surrendered the decision to atmospheric uncertainty. History has already shown what this kind of ending can look like. Skylab, the first American space station, re-entered Earth's atmosphere in 1979 after solar activity increased drag more than earlier plans had expected. Controllers changed its orientation and made limited adjustments, but the station had no complete capability for a targeted ocean disposal. It broke apart during an uncontrolled re-entry, with debris falling across parts of Western Australia and the Indian Ocean. No one was injured, The event became famous partly because the precise location remained uncertain until near the end. Skylab was much smaller than the International Space Station. The ISS carries far more mass, extends across a much wider structure, and includes materials assembled during decades of missions. Allowing it to repeat the same kind of uncontrolled return would create a greater and less acceptable risk. The comparison also shows how solar activity can change an orbital lifetime. Skylab did not descend according to one simple schedule written years earlier. The upper atmosphere changed, drag increased, the planned time available to rescue or reboost the station disappeared. The ISS is watched with better instruments and supported by more capable spacecraft, but the atmosphere remains variable. No tracking system can make an uncontrolled fall fully predictable. Only propulsion can turn prediction into guidance. This is why the final years of the station cannot be managed like the loss of a small satellite. A satellite may be allowed to decay naturally when the probability of surviving debris reaching people is low enough. The ISS requires a different standard. Its mass, size, structure, and orbital inclination make a random return irresponsible when a controlled alternative can be prepared. The goal is not to prevent re-entry forever, but to choose it, and that choice begins before the final engine burn. The station can be allowed to descend gradually while it remains controlled, using natural drag to reduce the enormous amount of energy that would otherwise have to be removed with propellant. Crew operations can end, equipment can be secured, and vehicles can be positioned while control is still reliable. The orbit can be shaped so that the final destructive pass occurs above a remote part of the ocean, far from major shipping routes and populated land. The atmosphere that spent decades threatening the station's altitude can then become part of the disposal plan. Natural drag can do most of the slow work, while engines provide the final decision. This is very different from simply stopping reboosts. In both cases, the station moves lower, but only one preserves the ability to choose the final path. In one, its future position is watched, its orientation is managed, and propulsion remains available until the critical moment. In the other, every orbit removes not only altitude but choice. Control is what separates a planned descent from an accident. The station does not need to remain inhabited until the final moment, but it must remain commandable. Power must reach the necessary systems, communications must continue, and navigation must remain accurate. The vehicle responsible for the final burns must stay attached and capable of producing enough force. The structure must survive long enough to reach the planned entry corridor. A controlled deorbit is therefore not one final command sent to an aging station. It is an extended mission whose purpose is destruction rather than research. For decades, the ISS has been kept away from Earth through reboosts. Near the end, the same knowledge of orbital motion will be used in reverse, and burns will no longer restore altitude, but lower it. Instead of making the station miss Earth again, controllers will shape the path so that the atmosphere finally catches it at the chosen time and place. The station has always been falling, and the final operation will decide when that fall is allowed to reach the planet. Until then, every maintained orbit preserves the possibility of a safe ending. Each successful reboost keeps the station useful, each tracking update keeps its future known, and each docked vehicle adds another layer of control. The ISS has not remained above Earth because falling was impossible. It has remained because humans continued interrupting the natural descent before it became irreversible. When that work ends, gravity and drag will finish what they began. The important question is whether they will finish it alone. And once the uncontrolled path had shown why the station could never simply be abandoned to choose its own final orbit, its return to Earth became not an accident waiting to happen, but a last maneuver that would one day have to be planned with extraordinary care. For most of its life, Every major orbital correction has carried the International Space Station away from the atmosphere. Engines have added forward speed, raised the path, and returned some of the altitude slowly taken by drag. The purpose has always been to make the station miss Earth again. Its final mission will reverse that logic. The same understanding of orbital motion that kept the ISS above the planet will eventually be used to guide it downward. The engines will not fight the fall. They will shape it. This ending cannot begin with one sudden command. The station is too massive, too wide, and too complicated to be treated like a small satellite. Its modules, trusses, solar arrays, radiators, docked vehicles, tanks, experiments, and internal equipment form a structure assembled across decades. No heat shield was designed to carry the full station through the atmosphere. The final return must therefore be prepared while control is still reliable. NASA and its international partners plan to use a combination of natural orbital decay and carefully timed propulsion. The upper atmosphere will perform much of the slow work, removing energy from the orbit just as it has throughout the station's life. Controllers can allow the altitude to decrease gradually, rather than spending an enormous amount of fuel to force the station downward from its normal operating height. But natural drag cannot choose the final destination. Its strength changes with solar activity, atmospheric temperature, station orientation, and altitude. It can lower the ISS, yet it cannot guarantee that the last paths will occur above an empty part of the ocean. Propulsion provides that final control. NASA selected SpaceX to develop and deliver a dedicated US deorbit vehicle, a spacecraft intended to remain capable of moving the full station during the final phase of its life. The vehicle is not simply an ordinary cargo craft, assigned one larger burn. It must provide far more propellant and thrusting capability than routine reboost operations require, while remaining gentle enough for the station's long and flexible structure. The ISS weighs hundreds of tons, yet the force must be applied through docking connections built for a complex structure rather than one compact spacecraft. A poorly controlled burn could create unwanted motion, structural stress, or a final path that no longer leads towards the target region. The deorbit vehicle must push long enough to make the result unavoidable, but predictably enough that the debris footprint remains inside a remote area. Before that final burn, the crew will have already returned to Earth. The station that remained continuously inhabited for decades will become empty for the last part of the descent. Cabins once filled with conversation, fans, experiments, alarms, meals, and floating equipment will continue circling without people. The station will still look alive from a distance, but its purpose will have changed completely. Power must continue reaching navigation, communication, and control equipment. Ground teams must know the real orbit closely enough to time the final maneuvers. The last phase will be a controlled operation, not a passive wait for gravity to finish the work. The station will begin losing orbital energy more quickly, but it will still circle the planet at enormous speed. It will not hover lower and lower above one location. Small burns can adjust the orbit so that the destructive re-entry occurs above a remote, uninhabited region of the ocean. The station cannot be aimed toward one exact point like a falling stone. It will break apart high in the atmosphere, and the surviving debris will spread across a long region. Controllers therefore target a footprint rather than a single impact location. The goal is to place that entire footprint where the risk to people is extremely low. A delay of only a few minutes at orbital speed can move the station thousands of kilometers along its path. The correct final burn must occur at the correct position, while the station is oriented properly and the atmosphere is understood well enough for the expected entry. Engineers will calculate a corridor wide enough to contain the likely variations, then place that corridor above empty ocean. Once the large re-entry burn begins, the station's forward speed will be reduced in a carefully chosen way. The path that once curved safely around Earth will dip deeper into the atmosphere. The station will still be falling forward, but the planet will no longer curve away quickly enough beneath it. For the first time since the earliest modules reached orbit, the ISS will be placed on a path designed to meet Earth. The initial contact with denser air will not look like the final images of a spacecraft capsule returning home. Its solar arrays and radiators will meet increasing aerodynamic forces while the structure is still moving at several kilometers per second. NASA expects the breakup to occur in stages. The solar arrays and radiators are likely to separate first because they are broad, exposed, and connected to the central structure through long supports. The modules and truss can then begin separating as forces grow. Individual modules will lose structural integrity, their outer skins heating and melting until the equipment inside is exposed. Light pieces with large surface areas will slow rapidly and burn high in the atmosphere. Denser machinery and stronger structural parts can continue farther. A limited number of heavy or heat-resistant components are expected to survive long enough to reach the ocean. A controlled path places the surviving material where it can fall without threatening populated areas. The final debris trail may extend across a vast length of ocean, but it will represent only a fraction of the station that entered the atmosphere. Most of the laboratories, living spaces, cables, insulation, computers, containers, and external hardware will be consumed during re-entry. The largest structure ever assembled in space will disappear across a small fraction of one orbit. The ISS took years of planning before its first component was launched. Assembly required dozens of missions and spacewalks. Modules were joined, power systems expanded, laboratories activated, and new vehicles adapted to visit it. The station survived leaks, hardware failures, debris threats, solar storms, and the gradual aging of almost every major system. Its physical remains will descend into deep ocean, far from the people who built and inhabited it. Only smaller objects brought back during earlier missions, photographs, samples, documents, and parts removed before the final descent will remain available on Earth. It will remain in spacecraft designs, medical knowledge, materials research, life support systems, docking methods, international procedures, and the experience of keeping humans alive away from the surface for months at a time. The controlled fall will protect that legacy from ending as an avoidable accident. Allowing the station to drift would risk people on the ground and spacecraft still using low Earth orbit. A guided return accepts that the mission must end, then uses the same discipline that sustained it to make the ending responsible. The station began with controlled burns that carried separate pieces upward. Its modules reached orbit because rockets accelerated them sideways fast enough to fall around Earth. Visiting spacecraft spent years adding fuel, people, equipment, and energy to the growing complex. At the end, another spacecraft will use controlled burns to remove enough energy for the atmosphere to take the station back. The difference between survival and destruction will be a carefully measured change in velocity. Even the last descent will not be a simple downward fall. The station will continue traveling forward around the planet, crossing enormous distances while its orbit collapses beneath it. The solar arrays may continue producing power while the atmosphere is already becoming too dense for the structure to survive. Then, heating, vibration, and structural failure will overtake the systems one after another. The bright point that crossed the night sky for decades will no longer complete another orbit. The controlled re-entry will take place far from populated regions. There may be no public view of the station breaking apart, only tracking data, mission commentary, and confirmation that the debris reached the planned ocean area. The ISS will simply be gone from the sky. Anything placed in low Earth orbit becomes part of a temporary environment. No station can remain useful forever simply because it continues circling Earth. Keeping it above Earth required constant effort, but bringing it down safely will require equal care. The station's history can be understood as a long refusal to complete one natural fall. Every cargo vehicle helped preserve a world that could exist only while motion, machinery, and people remained connected. The title of the mystery now has a clear answer. The space station has not fallen back to Earth because it is already falling, moving sideways fast enough to keep missing the surface, while repeated engine burns restore the energy slowly stolen by the upper atmosphere. It remains above us, not through one perfect orbit, but through decades of corrections. Its apparent permanence is an achievement created from temporary solutions repeated with extraordinary precision. The station that spent its life falling around Earth will finally be guided into a fall that no longer misses. Until then, it continues circling in the narrow region where gravity, speed, atmosphere, fuel, and human attention remain balanced. From the ground, all of that complexity becomes one quiet light crossing the dark. Its orbit is stable only because instability is measured early and corrected before it becomes irreversible. For now, the International Space Station is still falling around Earth, still missing the surface, and still returning to the same dark sky, because people continue giving its orbit the small, precise pushes that allow the fall to begin again. Good night.